If you can hear me and see me, somebody give me a thumbs up that you all can hear and see me. All right, cool. Before we get going too far in our lesson, I want to let you guys know that your binders are at the school. They are on a table right there on the school. 7 of you are taking it. They each have your name on them. So feel free to go by, grab that sometime this week. You don't have to submit anything to me. The only thing you have to do is just simply, or you don't have to bring any work with you because you're going to submit all that PDF style. Okay, so 27 through 30 homework, I want you to submit PDF style. Okay, that is that. And so they're there ready for you. The school's open from like 8:30 to 4, something like that every single day within that. So, yeah, not a problem at all. Just want to try to prepare you as best I can. Normally we would do this and it would be a lot different type binder, but it is what it is. So just to show you, I'm going to take the dock camera out. So just to show you, on the left-hand side, since this is inside your binder, on the left-hand side, guys, this is a table of contents for all the work we've done thus far. So while you're taking the test, it is open note. If like for some reason you're like, oh man, what's the derivative of a trig function? You kind of know where that is. Okay, so derivative of 10 function. Lesson 10, just go hunt down lesson 10 if you need to see something. All right. So table of contents here, it has the page numbers where it would be in our manuals, which at the bottom. Over here is just kind of like the welcome note and the format of the practice test. All right. So I said, please review the schedule below for the dates of our practice test. I have the schedule down here at the bottom. And then, so basically at the start of the practice test, I want you to set a 25-minute timer for part A. Start the timer and the test. And once you complete part A, take a 5-minute break, then set a timer for 15 minutes for part B, and then start the timer and start the test. Okay. You have nicey fancy tabs here that say test 1 and stuff. I didn't put those in mine. So again, you'll see test 1 part A, set your timer for 25 minutes, hit start, and then turn the page. Here's practice AP exam A. Okay. Here's your question. You answer it all down here. Should be enough room. If not, get another piece of paper. Then you stop after that. Oh, sorry. And you go to test number 1, part B. 15 minutes to answer that. Okay. Now, part A and part B are going to kind of be a little bit similar questions. I don't anticipate that on the exam, but just for the purpose of getting you more exposure to questions like this, because I think overall that their questions could be like kind of similar to this. So, so that's why A and B kind of look a little bit similar. But then once you go to test 2, you're going to see test 2 is going to look totally different from the test 1. Okay? So just trying to prep you in with some advice from others about what's the best possible thing for you guys to do. In the very back of your binder will be all your work that you turned in before. Okay? Will be all the binders that you have turned in before. Okay? Or I meant the homework. I think it was like 22 through 26 or something like that. All right? Let me straighten this back out. Okay. Any questions about the binders? Any questions about the binders? And I did say in there, sorry, I didn't read that part, but I did say in there, I know some of you have to work, all right? I know some of you several of you have to work, so you won't be able to like do it in the same time set as us, okay? But if you do, still use the timer to time yourself just to set the pace of the test, all right? So if you can't take the test on Sunday at 1 o'clock, that's our schedule. If you can't be there Sunday at 1 o'clock to take it, then whenever you go and watch it, okay, whenever you go and watch it, that's when you want, sorry, I just got a text message that I read. Whenever you go and watch it, before you watch the review of the test, take an hour before, take 25 minutes, 5-minute break, 15 minutes, and then watch the recording, okay? So as we've discussed, your schedule's kind of there. You all know it. So this upcoming Sunday on May 3rd, guys, we have a practice exam. I would love the fact that if all of you could be there at 1 o'clock, be sitting at a table in a quiet area, boom, you start it immediately. You can have your notes, you can have everything there. And then you work your 25 minutes, 5-minute break, 15 minutes, and then not shortly after that, 2 o'clock, I'll come on and I'll work the whole problem, parts A and B with you. Shouldn't take us more than 30 minutes, I would assume, to work through it. So shouldn't be that bad. Give me a thumbs up if you're with me on how the practice exams are going to work. Again, if you can't make these times, still time yourself and then watch the recording afterwards. Cool. One more thing I forgot to mention to you in the whole binder portion of all this. Oh. Is the fact that for each test, I went ahead and gave you the solutions so you could have them in front of you. Now, again, the solutions may not mean much to you, but we will work through it, okay? So, again, for part A here, I'm looking at my solutions, okay? Now, these solutions may mean something to some of you, but maybe the explanation when I explain it may make a little bit more sense, okay? So, you do have the exam solutions for all tests there. I would not encourage you to look at those until like afterwards as we're kind of going through it together, okay? But I did want to include those so you have those, all right? Again, just trying to prepare us in every way possible for these 2 questions. Before we go to 30, are there any questions over the homework from the previous night? No questions? Over 29 homework? Pretty straightforward. I cannot find mine for anything. Somewhere around here. Wow, I have so many papers. So much for that. Oh, there it is. So, hey, key thing that I'm looking for when you scan this to me, guys, is this right here. That make sure you went through each part, did the left, right, midpoint, and trapezoid. Okay? Make sure you went through each one of those with each one of these. All right? So, I'll show you my backside. So I just did number 1, part A. So using the left Riemann system or sum, the right Riemann sum, the midpoint, and the trapezoid. Okay, so this probably gonna require a little bit of work here, and I hope you guys already did it. If you did not, make sure you finish that up. Okay, so, and that's A through D. Make sure you show all work for that. Here is number 2. Just kind of showing the work for that. Number 3, showing the work for that, and number 4, and showing the work for that. Okay? All right, so let's jump to our last lesson, guys. The last lesson of this calculus class. I hope that's as exciting to you as it is me. Kind of short story. If you do see my blue finger here today, I'm actually working on my yard, and I got these chemicals offline. I actually bought the chemicals from eBay, and it's actually the name of the chemical is tenacity, but it's obviously it's a clear liquid, and you mix it with water. So they suggest putting blue dye into your sprayer, so when you spray it, you know what you sprayed, because if you spray too much, you could kill the grass. I'm just trying to kill weeds, but if you spray too much, you kill the grass and the weeds. So not sure what it's going to look like out there, but I could have just basically torched my whole grass. Don't know, but I did get a ton of dye all over my fingers and stuff, so I don't want you to think that I got just some nasty hands rolling around. Okay, Morgan's thrilled. Get out of here, Macy. I'm thrilled that this is the last one. Then we kind of prep for the AP exam. So it's been a fun ride, and I'll probably share a little bit more about this class with you guys later before it's all said and done. All right? So, the fundamental theorem of calculus. So far in calculus, we have learned 4 major concepts: limits, derivatives, indefinite integrals, and definite integrals. We have seen that a definite integral represents an area under a curve. The question is, what do definite integrals have to do with derivatives? We know there's some kind of connection there. The answer to that is what is known as the fundamental theorem of calculus, or FTC. It is a theorem that links the concept of derivative of a function with the concept of the function's indefinite integral. It also states that the definite integral of a function can be computed using any of its infinitely many antiderivatives. So, the fundamental theorem of calculus, FTC, simply states that if f and big F are continuous functions defined on a closed interval AB, and if the derivative of big F of x is equal to f of x, then the definite integral from a to b f of x dx is equal to big F of x on this, what we're going to call this limit, lower limit, upper limit, is equal to f of b minus f of a. F of b, upper limit, minus f of a, lower limit. Okay? Now that doesn't probably make too much sense to you right now, but give us a little bit and we will discuss that. Now, due to the timing of our class and the amount of time that's been taken away, and there's tons of proofs on FTC and why this all works out naturally. That's not going to be our number one concern today, is the proof, but we can go into like a little bit more of an informal proof. So we will not formally prove FTC. Most calculus books and websites on the topic have proofs. What is below is an informal proof that shows the link between the definite integrals and derivatives. So we start with a continuous function, f of x, as shown to the figure on the right. Each value of x has a corresponding area, f of x, representing the area under f of x between 0 and x. The function f of x, or big F of x, may not be known, but it is given that it represents the area under the curve. The area under the curve between x and x plus h, the light colored area right here, can be computed by finding the area between 0 and x plus h. Then subtracting the area between 0 and h. In other words, the area of the thin silver is f of x plus h minus big F of x. There is another way to approximate the area of the same sliver. If h is multiplied by f of x, we have the area of a rectangle that is approximately the same size of the light colored sliver. So f quantity x plus h minus big F of x is equal to f of x times h. So f of x times the height. This approximation becomes a perfect equal if we had the excess area as shown in the figure, so it follows. So f of x plus h minus f of x equals f of x h plus the excess. Now again, we're getting more into the proof of this and why this necessarily works. At this point, I'm not as concerned with you understanding this proof as much as you're just going to know how to basically find a definite integral today using the fundamental theorem of calculus. So as h approaches the fraction excess of h goes to 0, this occurs because the excess area is less than the area of the small rectangle. That small rectangle has the area of height times h and height times h is over h, which equals height. The h is canceled. As h approaches 0, the height goes to 0 as well. So f of x equals the limit h as h approaches 0, f of x plus h minus f of x over h. Now that should look familiar from the very beginning, guys. So this right here, this we know is the derivative of f. So f of x is equal to the derivative of big F of x. That is the derivative of the area of the function f of x is the original function. We discussed that kind of last period, or the last section when we were talking about, or maybe not the last one, but the accumulation function. We're building up to this whole theorem of calculus that f of x is equal to the big F, or the derivative of big F of x. So, finding the area under a curve and finding a derivative are inverse operations. So that's where we need to get to right here. That's kind of above it's the proof behind it. And that's basically our fundamental theorem of calculus, that finding the area under a curve and finding a derivative are inverse operations. And that is the crux of the fundamental theorem of calculus. So if someone was to ask you, what is the fundamental theorem of calculus? The main part of it, the fundamental theorem of calculus, is that finding the area under a curve and finding the derivative are inverse operations. Okay? If you're finding a derivative, okay, you're basically doing the inverse of finding the area under the curve. If you're finding the area under the curve, you're doing the inverse of finding the derivative. All right? So it's just one of those things you need to put in your memory. I have a lot of people ask, because people always forget what logarithm is, you know, and logarithms are just the inverse of exponentiation. When you have an exponent raised to a power, a logarithm is just the inverse of it. Well, what is the fundamental theorem of calculus? Is that finding the area of the curve is just the inverse operation of finding a derivative. Okay? So, that's all the meat. Now get to the work. So, here we go. Give me a thumbs up if you're on the back. We're ready to go on finding definite integrals. Okay. Now, so how this differs from before, guys, is before we either had the graph, right? It was like going up in a semicircle and then going on. But, hey, give me 2 seconds. I got to find my charger. Sorry about that. Didn't want to dial on you. So the difference was before is we had, when we were calculating derivatives before, we would have something like this right here, or when we had the definite integral and we're calculating all these areas, okay? Find all those areas. Then we moved to, then we moved over to the Riemann sums, and when we had that, we had a function and we had an interval, but we did it based on rectangles, trapezoids, left Riemann sum, right Riemann sum, stuff like that. But now, only thing we have, guys, is the definite integral sign and the function. And it wants to know, here's what it's asking. What is the area of x squared? We all know x squared is the parabola. What is the area from 1 to 2 of that? Okay? What is the area of x squared 1 to 2? All right? So, here is going to be our process in doing that. Okay? So, what we are going to do, guys, again, finding the area, okay? Finding this area here of this, going back to what is the fundamental theorem of calculus, find the area is the inverse operation of taking the derivative, okay? Now, in order to do this, our first step is to find the antiderivative of this, all right? Now, antiderivative, you may have to go back and look at your notes a little bit to kind of remember those antiderivatives, okay? So, this right here, we're going to find the antiderivative. First step, find antiderivative. So if you guys can remember, when you have something like x squared, you add 1 to the exponent, and then you put whatever the number that is in the denominator. So the antiderivative of x squared would be x cubed over 3. Okay? Then we're just going to set this up now, and this is just kind of the fundamental theorem of calculus right here, just following those steps from kind of the beginning. So first thing we're going to do, find the antiderivative. All right. Now from here, this is where we say f of b minus f of a. And that's a capital F, sorry. Now, let me just take us back here, guys. Okay? So, this is where we're getting this from. F, the derivative of big F of x is equal to f of x. Okay? So, here's what we're saying here. This f of x, okay, is the same thing as the derivative of f of x. So, we're putting that here. Okay? So, this becomes, once you take the antiderivative of this, it becomes this big F of x. And then notice a and b stay the same right here. And then that's equal to f of b minus f of a. Alright? A way you could think about it is like this right here. We could almost think of that as being like putting almost a tick mark there and being the derivative. Okay? But don't, it's kind of like, well, what I was saying is more like f prime of x here. It's almost like that there. That wouldn't be the derivative of big F, okay? So, in order to, the fundamental theorem of calculus would be just to take the derivative of this right here, which is big F of x, okay? And then just do f of b minus f of a. So, we've taken the derivative of this, of x squared, it's here. We put our a and b in place, and now we just say f of b minus f of a. Now this is our b, and this is our a. So f of b minus f of a, f of b would be this, guys. Put a 2 in there. So 2 cubed over 3. And that would be 8 over 3. And then f of a is 1, put a 1 there. That's 1 cubed over 3, which would be 1 over 3. And you're going to subtract those. And then we get 7 over 3. So the area under the curve of x squared from 1 to 2 is 7 over 3. Give me a thumbs up if you have your calculator. You guys have your calculators? Okay, cool. Let's actually, so there's a way we can do this on the calculator as well. All right, so here we go. Calculator. Here's what we're going to do. We're going to go y equals, and we're going to type in whatever our function is, x squared. Okay, type in our function x squared. Then from there we want to hit graph. So we have the beautiful x squared parabola. And what we want to do, guys, is this right here. Let's get the window closer here. So I'm going to hit window. I'm going to change my x-min to like -1. Change my x-max to like, I don't know, 6. Go up by 1. Y-min, I can take that to like -1. Y-max like 6. Okay? So then I graph and I'm seeing something like this right here. All right? Now here's what I want to find. I want to find the area from 1 to 2. Okay? Now, again, we know that we could do that with Riemann sums. We can find, okay, we know that the base is 1 and we could go up, find our heights, do a trapezoid we could, just by finding the height of the 2, whatever 2 is, which we know here would be 4. So there is that possibility of doing that, okay? But now, since we know the fundamental theorem of calculus is just simply taking the derivative of this, right? And then just saying f of b minus f of a based on our upper and lower limits. But with the calculator, the only thing you got to hit, guys, to figure out this is hit second. Hit second right here. Second. And once you hit second, hit calc or trace. And do you see number 7 down here? Number 7 is what we're looking for. And that's what we want to do. Okay? Hit 7. Now, notice what it asks you. It says, what's your lower limit? Well, our lower limit is 1. So we're going to just type in 1. You could trace to it on the thing, but just hit 1, and that's so much easier. Hit 1 and hit enter. So that's our lower limit. And then what's our upper limit? Our upper limit is 2. So we say, actually I should probably be pointing up here, 2. And I hit enter. It gives me the area. It shows me the area on the graph, as well as it gives me the area. You all might not be able to see it on mine, but you should be able to see it on yours that says 2.333333, and that is 7 over 3 as a decimal. If I was to do that again, if I was to clear that out and just do it again, x squared, just to make sure you're all with me, and I was to go to the graph, I changed my window, I just hit second calc, guys. Second calc, I hit 7, I name my lower limit, which is 1, enter, I name my upper limit, which is 2, enter, and then I have that, and that is my function. Now, of course, that's using the calculator, but we want to know the algebraic way as well. So easy way to check with your calculator, but let's step back into the algebra way. All right. So first step, find the antiderivative. We do that. And then second step, do f of b minus f of a. Okay? Now again, purpose behind it. Remember, fundamental theorem of calculus. What is this saying for you to do right here? This is literally telling you, find the area under the curve of x squared from 1 to 2. So keep in mind, the inverse operation of the opposite of find the area on the curve is taking a derivative. All right? So, and we know the opposite of taking a derivative, or excuse me, we know that taking the derivative here would mean doing the antiderivative of this right here. Okay? Again, fundamental theorem of calculus is saying the area under the curve. It literally reads the area under the find the area under the curve and finding a derivative are inverse operations. So we take the antiderivative in order to find the area under the curve. Then do f of b minus f of a. Jumping over here to number 2. 3x squared minus 2x minus 1. So again, remember with the 3x, we'd write that. You can bring that constant out and just say 3, and then x cubed over 3. And then minus 2x squared over 2 minus, just remember when you have a constant, it's just going to be x. Now here, this 3 and 3 cancel, the 2 and 2 cancel, and I'm left with x cubed minus x squared minus x once I simplify that. Give me a thumbs up if y'all remembering how to do those antiderivatives. Okay, cool. Now we put our limit, and it's -1 and 3. Okay? Now again, guys, keep in mind that we have to say f of b minus f of a. So f of b would look like this. Okay? It would look just like this. We would have to say 3 cubed minus 3 squared minus 3, and then minus f of a, which would be minus the quantity of -1 cubed minus -1 squared minus -1. Okay? So notice that first one we just had 1x, so we just had to plug, f of b in, but you're going to have to plug it into every x when there's more than one x. So 3 cubed is 27 minus 9 minus 3, and then minus, and then that would stay -1. That would go to +1 there, but it's a -1 there, so -1 minus 1, and then that would be +1. So 27 minus 9 is 18. 18 minus 3 is 15. And then, of course, all these are going to change because that minus on the outside. So 15, and really we could just subtract those and get -2 plus 1. -2 plus 1 is -1, and then that minus, so I have 15 minus negative 1, which would go plus plus, which would give us 16. Sorry, I didn't have too much room there to kind of explain that. But again, 27 minus 9 is 18. 18 minus 3 is 15. And then if you, that's negative 1 minus 1 is negative 2, plus 1 is negative 1, and that minus negative 1 would be plus 1. So 15 plus 1 is 16. Now, check with our calculator. We can plug that in and say 3x squared minus 2x minus 1. Right? Graph it. Okay? And we're going from negative 1 to 3. So let's change our window just a little bit. Let's negative 3, bump that up to 8, 1 by 1s. Let's go to negative 4, y max 8. So just change my window a little bit so we can see the graph a little bit better. And then again, I just hit second calc. Second calc, 7. My lower limit is negative 1. My upper limit is 3. Okay? So I probably could have went a little bit more up on the y-axis to get the full area. Okay? But that's literally what we're looking at right there, guys. And as you can see, it says the f of x dx is equal to 16. Is this making sense? Give me a thumbs up. Calculators is a nice feature, correct? That's pretty nice that you can just jump into it like that. Helps you get a better visual, I think, of it. Good, Ian. Cool. All right. Going on to number 3. So the definite integral from 0 to 9 square root of x dx. So we can write this as most of you guys would know as x to the 1/2. So then to do the antiderivative of that, to do the antiderivative of this right here would be to say add 1 there, add 2 over 2. So that would be x to the 3/2 over 3/2, which goes to 2/3 x to the 3/2. And then once you get your antiderivative, you set your limits 0 and 9. And then we just say f of b minus f of a. So f of b, so 9 to the 3/2, that would be the square root of 9 cubed. So the square root of 9 is 3. 3 cubed is 27. Okay? So 27, so it would be 2/3 times 27. (27) times 2 is 54. 54 divided by 3 is 18. So f of b is 18, okay? And then obviously, guys, if I plug in 0 here, it's just going to give me 0. So it'd be like 18 minus 0, which is just simply 18. Again, if we check that on our calculator, this would be pretty easy. Square root of x, we graph. May want to go zoom 6 here to zoom to your standard window. And then we just want to hit second calc. Second calc, 7. My lower limit is 0. My upper limit is 9. Gives us that right there. And our, as you see, the area would be 18. There is another way you can do it from the home screen. You can calculate that limit from the home screen. You just go to math, guys, hit math, and then you just go to 8 down there. Hit 8. Nope, that's derivative. Go math and go 9. It's 9, sorry. And then that sets up your interval, and then we just type it in 0 and 9. Yeah, and then we just say the square root of x dx. And that will give us our 18 as well. Okay. Okay, so a couple of different ways to easily check these in the calculator within that. All right. So number 4. 5 to definite integral from 5 to 10, 2 over 3x squared dx. So what we need to do here is just push that x squared up to the top. So it would look like this, 2x to the negative 2 over 3. Then think about it like this, 2/3 to the side, and then we're going to say x to the negative 1, right? So x, and when we add 1 to that, x to the negative 1 over negative 1. And then, of course, that x down, this x down here will push to down here. So that would give us 2 over 3x, and it's negative because that negative 1 right there makes the whole thing negative. So negative 2 over 3x. The x to the negative 1 was pushed down because it's negative 1 pushed down, and then it's just x to the first. 3 comes over, the negative goes out front. So that to that from 5 to 10. And we just say f of a minus f of b. So f of b, which is 10 here, negative 2 over 30. Excuse me. And then minus, and it would go out to be plus there. So minus would be a plus, and then 2 over 15. Then, if we set this up, negative 2 over 30 plus 2 over 15, we would make that go to 30, which is doubling that. So that would be negative 2 over 30. Negative 2 plus 4 would be 2 over 30, which is 1/15. Give me a thumbs up. You still with me, guys? Give me a thumbs up. Everything making sense? All right, cool. Carter, on that next one, there's no chain rule for antiderivatives, so go ahead, just for old time's sake, go ahead and FOIL that out for us real quick. What is number 5? What's this 2x minus 1 squared? What is that FOILed out? There we go. 4x squared minus 4x plus 1. Very good. Then from there, guys, we just need to say 4x cubed over 3 minus 4x squared over 2 plus x. That's our antiderivative, so we can say upper limit is 1, negative 1. So here's how this would look. If I I go f of b first. I go to b. Again, keep in mind this is b, this is a, so put b in first. So that was just simply going to be 4 over 3 minus 2 plus 1. That's all f of b. Right? And then I say minus. Now I plug in negative 1. So if I plug in negative 1, that's going to be negative 4 over 3. And then still minus 2 minus 1. And that's all f of a. Okay? So then from there, 4 over 3, and then that would be, so I'm going to go ahead and distribute that. 4 over 3 minus 2 plus 1 plus 4 over 3 plus 2 plus 1. Okay? That would give me 8. 4 over 3 and 4 over 3 would give me 8 thirds. 8 over 3. Negative 2 plus 2 cancels. And then 1 plus 1 is 2. And that would be 8 over 3 plus 6 over 3, which is the same thing as 2, which is 14 over 3. Okay, moving to number 6. Assuming you guys are good. If ask me any questions at any time, guys. Moving to number 6. I'm actually going to rewrite this as x over x to the 1/3 minus 2 over x to the 1/3. I'm going to separate it. And then I'm going to move that x to the 1/3 up. So x times x to the negative 1/3 minus 2x to the negative 1/3. Now when I add 3 to that, that's going to give me x times x to the 2/3, which goes, think about that being 3 over 3. That would be x to the 5/3 over 5/3. Okay? Over here, add 1 to that, which is 3 over 3, and that's going to be negative 2x to the 2/3 over 2/3. That constant just stayed out of that, right, when you pull it down. Now to clean that up, we'll just flip that up, and we'll get 3/5 x to the 5/3 minus 3 x to the 2/3, going from 1 to 8. Then we plug our upper limits in. If you plug an 8 into this right here, trying to see where I'm at. Okay. So if you plug an 8 into this right here, the cube root of 8 is 2. 2 to the 5th power is 32. 32 times 3 is 96 over 5. So 96 over 5 minus, and then if I plug an 8 into this right here, the cube root of 8 is 2. 2 squared is 4 minus 12. Okay, so that's f of b. Sorry, I don't have too much room here. Now f of a would just simply be 3/5 minus 3. 3/5 minus 3. So putting these together, that'd be 96 over 5 minus 12 minus 3/5 minus 3. So that would be 96 over 5 minus 12 minus 3/5 plus 3. That'd be 93 over 5 when I put those two together, and then minus 9. 9 is the same thing as 93 over 5 minus 45 over 5. 45 over 5 is 9. And then you subtract those and you should get 48 over 5. All right, moving on to the trig functions. From 0 to pi, 2 plus sine x dx. All right, so this one should be pretty simple. The antiderivative of this would just be 2x. And then don't forget your sine clock. Sine, cosine, negative sine, negative cosine. Okay? Don't forget this sine and cosine clock. Now to go clockwise would be taking the derivative. To go counterclockwise would be taking the antiderivative. Okay? So I want to find the antiderivative of sine, so go counterclockwise, so that would be minus cosine x. Now do that from 0 to pi. I do my upper limit first, so 2 times pi would just be 2 pi, minus cosine pi would be actually negative 1, right? The y coordinate, the x coordinate of 180 degrees would be negative 1, so that would become positive 1 right there with that minus there. All right, and then I subtract that from f of a, which is going to be 0 minus, and then cosine of 0 is 1. So that I should end up there with 2 pi plus 1. Okay? Here is our graph of that. Okay? So find that area there. 2 pi plus 1. Or, oh, I'm sorry, not 2 pi plus 1, 2 pi plus 2. My bad. Because 1 plus that 1 will be 2. Sorry about that. All right, jumping over here, same thing. We jump into that 4x, so we know that'd be 4x squared over 2, which is equal to just 2x squared, and then plus the antiderivative secant squared x. I would have those things open and available for you guys, your antiderivatives and your derivatives, when you take your test. So 2x squared, and then that is actually tangent x. From 0 to power 4. So I'll plug the first one in first, so that'd be 2 times pi over 4 squared, which would be 2 pi squared over 16. Because I have to attach the square to the pi and to the 4, and the 4 would go in the denominator from there. Or the 4 squared, which is 16. And then that'd be plus the tangent of pi over 4 would be 1. And then yeah, that's a 45. Pi over 4 is 45. So radical 3 over 2 over radical 3 over 2 is just simply 1. And then that would be minus, and then 0. And then tangent of 0 is 0 over 0. So that, or not, excuse me, is 0 over 1. So that would be 0. And actually be a plus there because that's plus. So f of a, or excuse me, f of b minus f of a. So simplify that down. Should be just simply pi squared over 8 plus 1. Last one. Give me a thumbs up. You're still with me? Cool, Maury. That's right. Okay, so now with this one right here, 4 minus 2x, to solve this algebraically, now you know with absolute value, it can run us like this, or it could run us as this, the quantity of this with a negative on the outside, just distributed in, which changes the signs. Okay, so what we want to know is for what value of this right here, 4 minus 2x, where is it greater than or equal to 0 at? Okay, where is it greater than or equal to 0 at? So we would subtract 4 from both sides and then divide by 2, which switches the sign, and I get 2. So this right here is going to work, this function is going to work 4 minus 2x when x is less than 2. So from 0 to 2, it's going to be represented by this graph, right? Or by this quote-unquote line, okay? And this happens because absolute value can be split into two different basically functions. So I can rewrite that as this. The definite integral from 0 to 2 will be 4 minus 2x. And I don't have to put absolute value because I'm breaking it down, all right? So that means this right here. So, and I can really say, and I can call that dx, and then just add that with the opposite of this. So from 2 to 5, it will be negative 4 plus 2x dx. Now, if you're confused on why we have to split it up, because keep in mind, if you had 4 minus 2x is greater than or equal to, let's say greater than or equal to 0, we would have to split it up into 4 minus 2x is greater than or equal to 0, and then negative quantity of 4 minus 2x is greater than or equal to 0. So again, here we get that negative 2x is greater than negative 4. You divide by that negative, we get 2. Over here, you would say negative 4 plus 2x is greater than or equal to 0. Add 4 to both sides, and you get that, and then you get x is greater than 2. All right, so when you would use this from 0, if our limit is 0 to 5, if our limit is 0 to 5, or not our limit, our integral is from 0 to 5, we're going to use this for 0 to 2. We're going to use this one, and which quote unquote mean that one, and then from 2 to 5 we're going to use that one because this represents everything from 2 to 5. All right, so then we just break them down, you know, like this. So get the antiderivative of this, so that would be 4x minus x squared, right, from 0 to 2, and then take the antiderivative of this, which would be negative 4x plus x squared from 2 to 5. So again, split them up just like we did here, and then do the antiderivative and then evaluate those, both of those. So the upper limit, 4x, would be 8 minus 4. 8 minus 4 minus 0. If you plug 0 into both of those, you're going to get 0. Then over here, you'd have negative 20. And keep in mind, we're going to add those two together because we're just combining their areas together. So plus, and then that would be negative 20 plus 25. And then minus negative 8 plus 4. So all this is kind of together. So that's going to come out on this side to be 4. And then over here plus negative 25 plus 25 is going to be 5 plus 8, which is 13. And then that you got to minus that 4. So that would take us to 9. And then that would take us to 13 as my final answer. So 4 comes from this side, 9 comes from all of this, giving me 13. If I check it on my calculator, this is what it looks like on a calculator. So again, we used this line right here, guys, for the left side when it's less than 2, and then we'd use the other line for the other side. So positive 2x minus 4, so it looked like that. So that's our area. That's what we use for that. And as you, I don't know if you can tell, but it says 12.9999753, so which is 13. Okay, so just to kind of read through here, your TI-84 calculators are capable of approximating the values of definite integrals and can do it from the home screen or the graphing screen where you can actually see the area under the curve. I've kind of explained that to you. You don't even have to do it like that. That's a little bit older than what we have. So you can actually do it from your calculator now. And then to actually see the area, we've done that. And then how does the calculator find the definite integral? Like finding numerical derivative, the calculator approximates the definite integral. It uses a method to, but not superior to, Riemann sums. But it is not exact. For instance, it can easily be shown that from 0 to pi cosine dx is equal to 0. But the calculator shown to the right gets the answer, which is essentially, but not exactly 0. That is because the calculator is not actually integrating, but approximating. Okay? And guys, that is it for what we're doing this year in terms of the lecture. That is lesson 30 of all this calculus stuff. Man, it's been a ride. It's been a fun ride. Appreciate you guys so much. I hope you guys have learned a little bit in this class this year. I know I have learned a ton. I've learned a ton of stuff myself. And and they say the best way to learn something is to teach it. So I've learned a lot. You guys have helped me. You guys have been patient with me, so I do appreciate that. Again, I told you at the beginning of the year, the calculus teacher that created this curriculum told me that you're really not a good calculus teacher until about your 5th year. So I hope that it's been decent for you guys this year. And again, I'll share a little bit more of my feelings for the class later. I'll somehow get that information to you about how much you guys mean to me. It's been a cool 2 years. I hate that it has to end the way it ends. But you guys are taking it better than probably anybody I know. So that is that. That's a wrap. Besides when we start doing our studies, okay? But in terms of lecture, I encourage you guys to keep this binder. Keep this calculus binder. Take it with you to college, okay? Because you're going to, I can see yourself referring back to it. That's why I gave you a table of contents. That table of contents, you can go back and review, just so if you get in college, oh man, I forgot how to do that. Here's some notes. I'm sure you'll have some notes from college as well, but just always a good reference, okay? If you guys don't have any questions today, I plan to see you on Sunday, this Sunday, okay? Now notice, I don't know if you guys caught, but no lecture over the homework, okay? So we do have homework on chapter 30, but here's our homework right here. I think it's just one page. Yeah, it's just one page of homework. If you have any questions on that, reach out to me, guys. If you have any questions, just email me. We don't have to meet on Thursday to review this. Just if you have any questions, email me. If you need to Zoom, I can Zoom with you to discuss it. Whatever questions you may have. I would like you to get me all this stuff by the end of this week. I would appreciate that. I think I gave you a time. I think I said Thursday at 11:59. So try to get me 27 through 30 by Thursday at 11:59 p.m. Okay? Any questions of me, guys? Any questions of me? Okay. Seeing no questions, give me a thumbs up if you're good. This all makes sense. And if you are good, you guys can be dismissed today. Again, on Sunday, start your exam at 1 o'clock p.m. And then I'll come on here with 2 to review all answers and to just double check stuff with you. All right, guys? So see you here at 1 o'clock. I'll try to send a reminder. You guys have a good day. Again, won't see you for almost a week. Today's Tuesday, so I won't see you till Sunday. Make sure you start that test about 1 o'clock. Time yourself. Get into the pace of the test. Love you guys. If you need anything, hit me up. I'll stay here for a few minutes for questions if you have any questions. Hey, same to you, Colton. Thanks for a great year, man. We'll have one last kumbaya before it's all over, even if we can go to Six Flags sometime. Yeah, thank you, Alex. Have a good week too, man. This isn't the end, so know that we'll have some time together to reminisce about all the good times. We'll go down memory lane.